This is the day one lesson on stoichiometry, so the first lesson. This is doing what we call mole-to-mole conversions. So this is going to use skills that we've been seeing in the last few months, including balancing equations and using mole conversions. What stoichiometry allows us to do is look at a chemical reaction, and we can determine different quantities like atoms, molecules, liters, moles, or grams. If we start with a certain material and end with a certain material, we could look at if you start with X number of grams of oxygen, how many grams of water could you make? So what I'm trying to get at, for example, is if you were to build a trike, for example, a trike has a couple of requirements. The first thing you would need is 3 tires. So I'm just going to use T for tires. So if you put 3 tires together plus 1 seat, so I'm going to use S for seat, that you can create or make 1 trike, and I'm going to use TR for trike. So what we could do is, let's say you have 7 tires in your hands and 2 seats. What you are able to make from that is 2 trikes, because you have not quite enough to build a third trike, because you only have 7 tires and you only have 2 seats. And this is kind of what stoichiometry allows us to do, is look at if you start with a certain quantity, how much can you end with, and so on and so forth. So we'll kind of dive right into a set of examples. So the first skill that you need to look back at is, can you balance an equation? So in our first particular example, we have nitrogen monoxide, NO, plus O2, oxygen, yields nitrogen dioxide. So the first thing we need to do is add our coefficients to balance it out. So I can see right out of the get-go the oxygen are not balanced. I have 3 oxygen on the left, 2 on the right. So I need to balance out the oxygen on the reactant side or the left-hand side. I can't put a 2 in front of the O2 because that's going to keep spinning it through with odd numbers. So I'm going to put a 2 in front of the NO. That evens out my number of oxygen. That gives me a total of 4 oxygen on the left and 2 nitrogen on the left. So all I need to do is put a 2 on the product side and I have a balanced reaction. Remember that this blank spot in front of oxygen doesn't mean 0. It's implying that a 1 is there, and we just don't write the 1 in. Okay? So part A is just taking the coefficients, I should say, out of the balanced reaction to then interpret what we would need if this was like a recipe. So what this says is that if we have 2 moles of nitrogen monoxide, it will react with 1 mole of oxygen. Where I got that 1 from is from the coefficient in front of the O2. It will produce 2 moles of NO2. And again, that 2 came from the coefficient from our balanced reaction. So B and C are true stoichiometry conversion type problems. So let's go ahead and take a look at what we need to do with these. In example B, it asks how many moles of NO2 will be produced if 3.6 moles of oxygen are used. So the first thing I can do is identify my given, just like we've been doing all year long. So the key thing, like I started to emphasize in the mole unit, is not to only identify your unit of measurement, but of what. And this is why it's important. And this will be the unit that we start really keeping track of that. The thing it's asking me to do is solve for moles of nitrogen dioxide. So my unit of measurement's the same. The quantity measurement is moles. What's different is we are going from oxygen to a different substance, and this different substance is the NO2, the nitrogen dioxide. So I can take my given, 3.6 moles of O2, and again, you want to label it with what it is. It'll make everything else go much more smoothly for you. The next part that's new for us is we have to develop what we call a mole ratio. And a mole ratio uses the coefficients from our balanced chemical equation to determine the proportion between the 2 elements or compounds that we're working with. So we, again, are looking at oxygen and NO2. So what I'm going to do is look at my balanced equation and find their coefficients. Coefficients represent a measurement, and they represent the number of moles. So again, our balanced equation shows that if 2 moles of NO reacts with 1 mole of O2, we get 2 moles of NO2. The problem is asking me about oxygen. So looking at my balanced equation, it tells me that I have 1 mole of oxygen, and it wants me to change it to NO2. Looking at the balanced chemical equation, my coefficient in front of NO2 is 2. So that represents 2 moles. This is my mole ratio, and this is my conversion factor between these two, again, elements or compounds. So we go ahead and set up our conversion factor, and again, using the same technique. The part you have to be careful of is both of these are moles. So the identity is what decides how to set it up. Because my given is oxygen, my moles of oxygen are what's going to go in the bottom of my conversion factor. So in the bottom will be 1 mole of O2. In the top will be my 2 moles of my NO2. I can see that moles of oxygen eliminate, and I'm left with moles of NO2. So all I need to do to solve is multiply, and 3.6 times 2 will give me 7.2 moles of NO2. Let's go ahead and take a look at example C now. It asks how many moles of NO must react to form 4.67 moles of NO2. Again, I can identify my given, so I'm working with 4.67 moles of NO2. We're now solving for moles of NO. So again, for both these style problems, we are staying in the unit moles. It's the identity of the material that we're looking at the ratio of. So I'm going to go ahead and write my given out. So 4.67 moles of NO2. I know I'm going to need a conversion factor. Again, the conversion factor, like in this problem that I'm boxing in, is the mole ratio. You don't have to write this out every time. You can go ahead and substitute right into your equation. Because my given is moles of NO2, when I take a look at my equation, this is my coefficient. So that means 2 moles of NO2 is going to go in the bottom. The problem is asking me to solve for NO. So if I take a look at my top balanced equation, the other half of my ratio is 2 moles of NO. And I made a mistake here, and I just wrote out O2. It should be NO2. So let me erase that and change it over. Now, if you were talking to your math teacher, they would probably tell you to simplify your coefficients, thinking of it like a fraction. We don't really need to worry about it. The math works itself out. So if you take 2 divided by 2, that gives you 1. Then we multiply it by 4.67. So our final answer for this problem is 4.67 moles of NO. Moving on to the next example, we now have the reaction between ammonia, oxygen, to make nitrogen gas and water. To balance this one, when I start looking at it, I can see my nitrogens are in balance, so I can go ahead and place a coefficient of 2 here. That gives me 6 hydrogen on the reactant side, so to take care of that on the product side, I'm going to place a coefficient of 3. What I can see the issue is now is when this distributes through, that gives me 3 oxygen. So this is one of those situations where we need to double. So what I'm going to do is change my amounts to make it an even number. So I'm going to change this from 2 moles of NH3 to 4. And I'm going to change my coefficient on my water from 3 to 6. And that makes things easier to balance. Got to update my nitrogen because I now have 4 on the reactant side. I'm going to put a 2 here. So the last thing to take care of oxygen is I have 6 on the reactant side, so I'm going to put a 3 here, and I now have a balanced equation. So looking at example A, I have 20 moles of ammonia, NH3, and it wants to know how many moles of water is that equal to, okay? So we have our given, so I'm going to write out 20 moles of NH3. It wants me to change it to moles of water. So I need my mole ratio, again, the relationship that comes from our balanced equation from above. Looking at the problem, I can see my coefficient in front of NH3 is 4. So I have in the denominator 4 moles of NH3. It's talking about water. Looking at my balanced equation, I have a coefficient of 6. So again, do not worry about simplifying your coefficients. And again, thinking of it like a fraction, we're not worried about simplifying. You can leave it as a 6 and 4. So to solve, what you're going to do is take 20 times 6. Then you're going to divide that answer by 4. When you do that, you get 30 moles of water. And again, looking at units, I can see moles of NH3 eliminate. I'm going to erase the balanced equation and rewrite it in to help us with example B. So again, our coefficients that were original is 4, 3, 2, and 6. Okay, so example B. It asks how many moles of nitrogen, the N2, will be produced if 3.5 moles of oxygen react. I've identified my given as 3.5 moles of O2. We want to know how many moles of nitrogen are going to be made then. So again, I need to go to my balanced equation to get my coefficients. Looking at oxygen, because that's my given, the coefficient there is 3. So in the in the denominator, we're going to put 3 moles of O2. We're looking for nitrogen. So looking at my balanced equation, my coefficient here is 2. To solve the problem, I'm going to take 3.5 times 2. I'm going to divide that out by 3. When I do that, I get 2.33 moles of nitrogen, because again, looking back at the problem, moles of oxygen eliminated. In class, we just did these first 2 examples, so this should give you a start on how to do mole-to-mole conversions using a balanced chemical equation.